Hello friends, welcome to my channel. Let's have a look at problem 2360, longest cycle in a graph. So as the title suggested, this problem is a graph problem. So in this video, we're going to share a solution based on depth first search to detect graph cycle. So this problem asks us to return the length of the longest cycle in the graph. If no cycle exists, we're going to return -1. So the constraints on this problem are mainly on the number of nodes and on self-cycles. So the number of nodes can be up to 10 to the power 5, and there are no self-cycles. So with that said, let's look at example 1. So example 1, the return is 3. So here is the cycle marked in red. So in example 2, actually there's no cycle, so the return is -1. Another important assumption in this problem is that each node has at most one outgoing edge. So this actually tells, so each node can lie at most in one cycle. So with that said, let's look at the method here. So the method is based on depth first search. So here the idea is very simple. We're going to use a widget index to retrieve if there is cycle and what's the cycle length. So the specific procedure is the following. So we're going to use a dictionary, let's call it check, abstract data structure, to record the node we visited as a corresponding incremental index. So for a current node with index d, for example, when we look at its neighbor, so if the neighbor not visited yet, so we assign the neighbor with index d+1 and then store this information. Otherwise, if the neighbor is visited, it means that we detected a cycle. So last time we saw the same neighbor, the index or the time is check MB, right? We can retrieve the information from the dictionary. So the cycle length would be d, the current index, minus the check neighbor. Last time we saw it, +1 because there's a cycle, like here. So let's do a walkthrough for example 1. So let's look at the node 3 with a start index 0. So you can actually choose any start, for example 1 or -1 even. So if we visit 3, so 3 we record the time that's 0, we visit this 3. And then we look at the neighbor of 3, that is 2. So 2 is not in the check dictionary. So we add 2 and 1 in the check dictionary. And then we look at the neighbor of 2, that is 4. So 4 is not in the check dictionary yet, so we add 4 with the incremented index 2 to the dictionary check. Then we look at the neighbors of 4, that is 3. So 3 is actually already in the check dictionary. It means that we find a cycle. So how we compute the cycle length? So current d is 2, right? So last time we saw 3, and the 3 is index 0. So we use this d value, current d value, minus the index last time we saw 3, that is 0. So 2 minus 0. +1 is because we need to add the edge from 3 to 4, because it's a cycle, right? So the total return is 3. So that's also the final result in example 1. So with the example walked through, so let's look at the plan. So in this video, we're going to present a DFS solution in recursion format. And in the next video, we're going to present a format like the find method in union find abstract data structure, which actually we practiced quite a lot. So now let's look at the solution. So we're going to divide the solution into different parts. So I'll split it into 4 parts. First part is I'm going to initialize an instance variable to update the result state. We're going to call this self answer, let's say, to be -1. -1 because of this requirement here. And next, we're going to find nodes, candidate nodes that can lie in a circle. So for a node to be in a circle, it must have non-zero in degree and non-zero out degree. So we're going to initialize two set, in degree and out degree. So we're going to find those nodes with both non-zero in degree and out degree. In other words, this is a set intersection operation. So let's see, for I, V in enumerate edges. So if V is not equals to -1, so this means that there is an edge from I directing to V. So in other words, the V has in degree. We're going to add V to the set, and I has out degree, so we're going to add I. So that's it for this check for in degree and out degree. So the potential candidates are those nodes with both non-zero in degree and non-zero out degree. So the candidates is nothing but in degree intersect out degree. Right. So this way we find the potential nodes that can be possible in a circle. So the third part will be a depth first search to detect circle and update the self answer or the instance variable. So for this, let's do this DFS. So this is going to accept three arguments. One is node, can be node 0, node 1, node n-1, and the current. So this is the index for this is the start of an index. You can choose it initialize as 0 or 1 or any other integer when you start. As long as it's a start, that's okay. And check is going to store the index or the time when we visit in node. So with that said, let's do this depth first search. For this purpose, I'm also going to initialize a big dictionary called visited. So this visited set will record the nodes we have already visited when we do the depth first traversals. So once visited, we do not need to visit it again. So with that said, let's see. If we visit the current node given by node, we first add this to the visited site. So anyway, we visited it, and then we're going to add this to the check node. So I'm going to use the current index as the time or index I visit this current node, and then we are going to look at the neighbor of this guy. Neighbor is nothing but edges node. So then if neighbor in check, it means that we found a circle. So then we're going to update the result. Self answer equals maximum of self answer and the current circle length. That is current minus last time we see this neighbor, then plus 1. So that's it. Also, we need to add this to the big visit set so that we don't visit it again. So then we are going to add a stop condition by using this return. So this is the one case. Another case is if neighbor not in visited and neighbor in candidates. So for this case, we're going to look at this neighbor, right, doing depth first search. So we are going to call this depth first search function itself, and then we pass it to the neighbor we are going to look at, and we increment the index by 1. And the dictionary, as it's mutable, its state is already updated. So we put the current state of the check here. So that's it for this hyperfunction. So once we call this function, so the instance variable will be automatically updated. So that's the step 3. So lastly, so we're going to do DFS and return result. So this is actually a routine. So for node in candidates, right? So we just do DFS. So node. So we can start from any node, any index. Let's put 0 here, just for. Then the initial state of the check dictionary is empty. Then we are going to return self answer. So that's a solution format for this following this idea. Let's do a special case check. Yeah, it passes example 1. So let's do a generic case check. Yeah, it passes all the cases. I guess that's about it for this specific format of solution. Please follow up on my other videos. Thank you very much.